Hello and Assalamualaikum warahmatullahi wabarakatuh. This is our final presentation for BNP 20203 Mechanics of Materials, and we are for Group 6, Section 1. Before we start, I would like to introduce our organization chart, or known as my group members. The first one is Muhammad Aidil Ashraf, known as our Chief Executive Officer. Second is myself, Farah Aisha, as Secretary. Third one is Kasdina Nakia as Engineering Consultant. And fourth, Nur Atira as Environment Consultant. So this is our short brief introduction to our company. Our company name is FKA Construction Company, and we are located at Arah 1 Jalan Pananjaya 1, Taman Pananjaya 81200, Bandar Baru Udah, Johor Bahru, and this is our company logo. Next is our project introduction. Our project is a pedestrian bridge and it is a truss bridge. Location of the project is at Lorong Jaffa, Kampung Bakri Muar, 84000 Johor, and the aim of this bridge is to connecting residential area to agricultural area.
The Warren Truss Bridge is a very well-liked type of bridge. We all agree that the Warren Truss design and concept is the best option because it evenly distributes the load across a number of members, which is one of its main advantages. The Warren Truss Bridge is extremely sturdy due to the use of rigid triangles in its construction. Furthermore, Warren Truss bridges use less construction material than the majority of other bridge design. It may be built piece by piece, which lowers the cost compared to conventional ones that call for the full framework to be in place before the building. This expands the number of patterns that can be used to construct the bridge. The view is not obstructed because the bridge is open.
Structure of Warren Truss Pedestrian Bridge. An alternate compression and tension diagonal truss are commonly referred to as Warren Truss by bridge historian and early textbook. By occasional it is referred to an equilateral truss because all panel length and diagonal are equal, resulting in a series of equilateral triangles. The long compression element in the top chart requires bracing to reduce buckling in the vertical direction as the span length and therefore the head of truss rise. The vertical in this instance are positioned from the lower chart panel point up to the midpoint of the chart member immediately above. Additional, as the deck structures shrink length, it becomes necessary to either use heavier member or to add vertical from the top chart panel location that descend to minimize panel length. The truss design that James Warren and Wilbert Munzani patented in 1848 in England are not either of these two. Their invention was based on truss of similar design that Alfred H. Naval constructed in the front, as well as patent issued to William Nash in England in 1839. The truss that Warren and Munzani designed may be utilized as a deck or through truss, and they were known English engineers. The lower chart member were made of wrought iron bar and link and diagonal, while the upper chart was made of cast iron. Cast iron connection block connected to the cast iron top chart member to the lower chart wrought iron member, and pin joined the cast iron diagonal to the lower chart wrought iron member. Construction of Bridge and Equate was the title of the patent application, and it was granted on August 15, 1848. The method of estimating load in a truss member under constant and variable load was published by Square Whipple in the United States, but it had not yet reached England. W. B. Blood didn't create a method of evaluating triangle truss like Whipple had until 1850, by Grid 2015. Okay, for truss. Comparatively to beam, truss are structural components that can support load over quick wide span. Having tension and compression component is a defining feature of truss. A lot of roof, floor, and bridge structure utilize this type of structure. Okay, there's 11 type of truss, which is Warren truss, Fink truss, Howe truss, Pratt truss, King post truss, Queen pot truss, Fat truss, Caesar truss, Fan truss, double Fink truss, and the last one is double Howe truss.
Next is the beam analysis related calculation. As was shown, the first table is the data about our project beams, and the second one is the calculation that were used for this analysis. The first one is lift load and dead load, diagram for FBD, SVD, and BMD. And next is inflection point, section properties of center and moment of inertia, section modulus, and deflection. Next is beam analysis for the related diagram. The diagram of free body diagram is an important step in solving mechanics problems since it helps to visualize all the forces acting on a single object. The diagram which shows the variation of shear force along the length of the beam is called shear force diagram, and the diagram which shows the variation of bending moment along the length of the beam is called the bending moment diagram. Shear force and bending moment diagrams are analytical tools used in conjunction with structural analysis to help perform structural design by determining the value of shear force and bending moments at the given point of structural elements such as beam. The centroid of the shape represents the point about which of the area of the section is evenly distributed. The moment of inertia are calculated with respect to the section centroid.
Now, let's move to the next analysis, which is the truss component. For our pedestrian bridge, we use the material hollow steels, where the compression is 30 kN meter cubic based on the BS table. The total load we determine is 0.48 kN and the stability for the truss is determined. We use this value to find the support reaction of the truss where all the total load is the same value. This is the table of all the value for every members in the truss we get, where it shows either the members is the tension or compression. For the last analysis is to determine the value of the maximum deflection and the maximum moment of the column component. We use the ready-mix concrete with the compressive strength is 30. Elastic modulus value we use is for 30 GPa. The yield strength is 50 MPa for the ready-mix concrete. The value we use to get the maximum stress is the bigger than the yield strength of the material, which is not appropriate the value. So, we assume the new value and finally we get the proper value lower than the yield strength, which is 50 MPa, and it is an appropriate value. Based on the new value, we can determine the maximum deflection and the maximum moment, which is the value is suitable for our pedestrian bridge. The critical load value is safe for an pedestrian bridge to be used. That is all from analysis. Now let's move to the conclusions.
In conclusion, FQA Construction Company's most recent project involved designing and constructing a pedestrian bridge. It was dubbed Old Street, has a length of 9 meters, a bridge deck span of 3 meters, and a height of 1 meter. It is situated at Lorong Jaafar, Kampung Bakri Muar, Johor. This bridge was built to connect and make it possible for pedestrians or villagers to travel from a residential neighborhood to an agricultural area. By using ready-mix concrete of grade M25 for the beam and the column material is made of ready-mix concrete of grade M30. The bridge deck is made of tantalized softwood. In order to implement the Warren truss design, hollow steel with high-tension steel bar is used in the truss, which has a length of 9 meters including the handrail. Following that, for information and better understanding, the report goes into detail about not only the parts required to build the bridge, but also all the related parties. Consequently, making the most effective use of the mathematical formula and apply force calculation. Following that, for knowledge and a better understanding, the report goes into great length to explain not just the parts required to build the bridge, but also all its related members. And with that, we end our presentation with a thank you.